what is the electron domain and molecular geometry of BrO2? So electron domain and molecular geometry of BrO2 minus. So this one is actually a doozy of a question, because bromine is actually a valence electron. I mean, not a valence, it's actually a halogen. I mean, it's already almost full, it only needs one more. But let's actually break down exactly what we do, because for this we actually do need to start with the Lewis dot diagram. And the way we figure out that is by actually, first figuring out how many electrons there are that we're messing with. So bromine has 7 valence electrons based on the fact that it's on the 17th column. And also you can also show it based on its electron configuration. You end up with 4s2, 4p5, which does add up to 7, the 2 and the 5. Oxygen, exactly, we know that it's a 2s2, 2p4, and also it's on the 16th column, so it's 6. But again, there's 2 of them, so that's 6 times 2, that's 12. And then the minus actually is actually just going to be plus 1 more electron. So that's going to be 7 plus 12, that's 19, plus 1 equals 20. You want 20 electrons in total. So now, because bromine is actually the one that's like, I guess, single, that's one I actually put in the middle first. Okay, I'm just going to say that's surrounded by 2 oxygens. Okay, now we want to make sure we fill in 20. So first let's do the double bond, the single bond here on each side. So we've accounted for 4 so far. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So luckily for us, we actually have exactly what bromine is going to be. And exactly, we counted it all. We have 8, 8, and then 2 more at the top. Okay, 2 more lone pairs. And we actually want to see if this is its favored stability. Although each one has 8 in the electrons, so bromine, as we know, exactly 7, which is the valence electrons. And now we want to subtract the lone pairs. So we have lone electrons, that's 4, plus the bonds, so that's 4 electrons in bonds, but divided by 2. So 7 minus 4 plus 6 is equal to 1. So this bromine actually in here is going to be actually plus 1. Okay, and then we do the same thing for the oxygens, but this time is 6 minus we have here 6 plus 2 over 2. Okay, that's 7 in total, so it's minus 1. So minus 1, minus 1. You technically want to be able to get as close to 0 as possible, okay? But technically for this one, if we try to get to 0, you would unfortunately end up with very unstable elements on the side, if that makes sense. So for example, if we try to get 1 electron over here to make it 0, because exactly it would now turn into 6 minus 5 plus 2 over 2, technically it would be 0. Okay, but this is now unstable, that just wouldn't work. So this, unfortunately, and I say unfortunately because you don't really see this in nature, is the most stable state for BrO2 minus. Okay, and exactly, you see that 1 minus there because of the fact that when you add up the minus 1, plus 1, and minus 1, you get in total just 1 minus. Okay, now that we figured it out, let's actually draw its shape. So with that being said, you have the bromine and you have its 2 lone pairs, and you now have the oxygens with its full shells. So actually, this right here is actually what you call a bent geometry. Okay, and I believe the angle is like less than 104, something like that, around there. Let me see here, because I wrote it down somewhere. For bent shapes, the angle you'll see is going to be around there. The lone pairs actually may influence the shape a little bit, but less than 109, so not 104, 109 degrees. Okay, but point being, right, actually the reason why we know it's bent, because this is actually just a much more complicated form of something that we're actually more familiar with. Water is also a bent shape, okay, because it has the 2 lone electrons floating above it, and it forms like that. This is also the bent shape, but this is exactly, we have the electron domain based on the Lewis dot diagram, and we actually have now the molecular geometry as well, so it's bent. Okay, exactly, and you need to accommodate one lone pair, at least one lone pair on the central atom bromine. Okay, if we try to do like a very strange let's see actually what happens here if we did this. If we made it a double bond, okay, because although now bromine breaks the octet rule, maybe now it will be that it's technically more stable because the negativities end up being like close to 0. We try to find out the what's that number called again? The electron. It's not an electron number, but it's not the electronegativity either. It's just the assigned number. But let's just try that same math. The bromine, exactly, it's 7 minus. So now it has still 4, but plus 3 over, 6 over 2, because now there's 3 double bonds in total, and that does actually equal 0. And for oxygens, you'll see 6 minus 4 plus 4 over 2 also equals 0. So technically, if it could break the octet rule, this would actually be its possibly more stable form. If I can just move everything up, this right here could possibly be its more stable form, but at the end of the day, you still have a bent shape. Okay, so this could be a possibility. Okay, I'm not gonna just throw it out, because when you try to actually do it, it's like now you have the numbers of 0, 0, minus 1, which is something that it may actually prefer if possible. Okay, so with that being said, I'm gonna let you look at this, take a picture of it, try to find out which stability it prefers. Might have to search that one up later, because I'm actually quite curious about how this BrO2 would work in nature. Let's move on to question 18 then. Okay, and this is correct because it does mention that it's bent, but they mentioned also could be linear as well. It's just bent. But yeah, so let's move on to now question 18. Okay,